myself started here. I do want to see how long I take. But no, there's not.
I can get it down to the second at least. So far.
Okay. Yeah. I'll try to be brief. That was the name of an editor that I didn't like. Anyway, one has to realize back at the time Lehmer was working on this, calculations were not easy. He published a paper after he had developed it about it in 1928. That paper is available on the internet, and Ed Thalen copied the entire paper. Delightfully, it's in two forms. It's translated to ASCII, but if there was any problem, Ed also has on that the photographs of the pages so you can see it in detail. Anyway, I want to talk to you a little bit about chains and something that you probably already know if you really think about it very much. But in detail here, these chains each have a different number of links. Each link position corresponds to another digit. So if you rotate the chain one link position, you've effectively added in one number. If you think about chains of, let's say, well, let me give you a little bit of detail. Each of these chains, and I'm quoting the paper more than what I see here, is on a sprocket that has 10 teeth on it. So that if you turn this shaft one revolution, you've actually advanced it through 10 digits. Okay? Yes, all of the chains have a starting position, position 0. And let's just talk momentarily about some chains to give you some ideas that really doesn't exist here. If you had a chain that had 10 links in it, if you turned that over, say, 503 times, the chain would have gone around 50 times and plus 3 more and stopped on the third one. So what this is really dealing with is the remainder of when you go through whatever number of links is in the chain. For those of you that have worked with computers, and I assume most of you have, you can think of that as a different number system base. If you had a chain with 11 links in it, you'd be dealing in number system base 11, and every time it went a full cycle, it would have left you with the remainder, number 11, last digit, or modulo 11, as some people like to talk about it. If you chains, let's assume that you had a chain on there with 10 links and another chain with 11 links. Take them to get back in synchronization. You start them out at 0, you start rolling this around. When the chain with 10 links is gone all the way around 10 times, your 11th one still lacks one. So you could actually, the thing won't get back into synchronization until it's actually gone around through 10 times 11, or that would be 110 times. If you put another chain on there with, say, 9 links, before they all went back into synchronization, you'd have to turn it 9 times 10 times 9, 11 times the 10.
You should mention prime factors.
Indeed. What this was all about, and why Lehmer made it, interest in the day was factoring numbers. And I think everybody here knows what factoring is, but I'll just say it to remind you. Factors are nothing but proper divisors of the numbers. If you have a number like 15, its factors are 3 and 5, and that's what Lehmer wanted to find with this. Most of us today would factor larger numbers simply by starting off doing divides. And you really only need to divide by the prime numbers, and you all know prime numbers are numbers that don't have any proper divisors. Another thing about this is that he was really only interested in factoring odd numbers. You don't go ahead and find 2 with a machine like this that divides into it. So we're only looking at odd numbers. The way most of us would do this is to start dividing by 3. If it don't divide by 3, you divide by the next prime, which is 5. You divide by 7. You divide by 11. And that gets rather long process when you're talking about numbers that have an impossible process if you talk about numbers that have 6, 8, 10 digits. And he was working on numbers that size. There is another technique which is really the basis behind this, And I don't have quite enough time here to describe it, but it is a technique that was developed by Fermat, and what he's trying to do is work the other way around. Instead of starting with the smallest primes and seeing if they'll divide, you want to start with some of the larger ones. Well, if you have a large prime number, the largest prime that you need to really worry about, I mean, a prime number, a number that you assume has factors and you want to find the prime factors of, if you could start fairly near the square root of that number. Going down the other scale, as it were. If you are dividing numbers in, you don't need to go beyond the, working up the other end, you don't need to go beyond divisors of up to the square root of the number. Now that technique assumes that there's two factors fairly close together, and they don't have to be terribly close together, but fairly close to the square root. Now you can think of the average of those two factors, or you can think of the difference of them, and because we're only interested in odd numbers, the difference between two odd numbers is always an even number, right? The sum of two odd numbers is always an even number. If that pains you, think in binary. Helps. Anyway, looking at these factors, the Fermat technique says, well, let's take the average of those numbers. You could call that A, and the difference between them, the average difference, or half the difference, would be B. And so any number that has factors could be A plus B times A minus B. Right? Make sense? If you multiply A minus B times A plus B, your algebra might remind you that you get A squared minus B squared. And what this machine is all about is helping him recognize numbers that are perfect squares. And that is not as difficult as you might think. You know, if you're trying to find factors of some large number, you don't know what the factors are, you might start guessing. Well, another approach is, say, we'll work from the other end, we'll try to guess at A's and B's. And so that's exactly what this machine was about. You can say that your number equals A minus B times A plus B, or it equals A squared minus B squared. And based on that, he put stopping pins in these chains at every place that there could be a possible square. And let's go back and think in base 10 for a minute. If you think of numbers that are perfect squared, base 10, the last digit of those will never be a 2. Right? Multiply 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, you never get a 2. You never get a 3. And so just by looking for numbers that are squared, we could cast out a whole bunch. It turns out if you look at the last 2 digits of numbers that you'd find if you just simply squared integers going up through 2 digits, you'd only find 22. There's only 22 last digits. It turns out there's never a 3. Any number that ends in 5, the digit that precedes it is always going to be a 2, 25. Any number that ends in 0, the last digit's going to be 0, 0. So what he did, in every one of these number system bases, he put a stopping screw. And it turns out if you're working in number system base 13, your chains are not going to be in sync like they are in 10, or they are in 17. And so the stopping screws won't line up as this thing goes round and round and round until you finally, and so what this does, it stops when it thinks it's counted up to a perfect square. And with a little bit of chalkboard and whatnot, I could show you how you take n plus the squares, and that's got to be another square. And when you find two numbers, a and b, that are both integers, and a minus b, a squared minus b squared equal n, you can stop and you've factored the number. I have gone for roughly
10 minutes.
9 minutes and 27 seconds.
Why don't you just briefly mention the other two?
Are there, well, let me just make a little bit more about this. How you would set a number in here. If you wanted to know where this chain should be set, let's say it has 7 links in it. You divide your number by 7 and then move it over to that position. The chain link, and by the way, it went up to 87. you'd divide, or 67, you'd divide 67 into your number. Whatever the remainder was, you'd set the chains at that position. That's how you set it up, and then you start it going. And through, by the way, each different number system base that you use cuts down the probability by roughly a factor of 2 that you will stop on a number that is not a prime. So by having 18 of these, the probability that it would stop on a number that was not a perfect square was basically less than 1 and 2 to the 18th, which is a pretty sizable number. And then he would go through and say, oh, it stopped. Is this number a perfect square? And by hand calculations, he didn't have calculators. This was all done in 1928. This machine ran the shaft at 300 RPM, giving him 3,000 numbers checked per minute. He made one with paper tape with holes in it. Logically the same mathematics, but it could run faster. And his ultimate, at least in this mechanical, was the gear machine, and I can't tell you how fast it ran. He actually had, I think it's 30 gears here with holes in them, and instead of a screw hitting a switch, it sent a light beam through, and when all 30 of those 30 different number system bases all agreed that this number is a perfect square, he would jump and sing and go off with his calculator and verify it was right and announce to the world he'd found a new factor for a new prime number, or a new number that was not prime, that was suspected of being prime.
Which one is the oldest?
I think they go exactly in this order. Now the paper that I read only describes this one, and one of the later papers talks about this. So that's an assumption on my part, and this machine does not quite agree with the paper. And for those that are interested in more detail, I have put on my website some more details about what I've done, tables about where you'd put the screws if you wanted to put your own, more details about perfect square numbers and looking at them in base 10. And if you know my first name, I was able to register that as a domain name, lafarr.com. If you put a slash after that and chain.htm, you'll get that paper. In there, there's a link that talks about the 1929 paper that is what I read to figure this all out.
It's also worth pointing out that that chain unit is in fact a copy made by students at Berkeley under Lehmer's supervision, whereas the other two are original.
Right.
I don't think the original chain machine still exists. I think somehow it's
And according to the paper that he wrote in 1928, the zero link on this should have all been painted red. I don't see any red links on here. And then the lengths of the chains don't quite agree, but every chain has lengths that are related to a prime number, starting with 2, 3, up through 67. And all those chains just won't stop unless they think it's a square, and that's pretty likely to be a square. He was factoring numbers, and by the way, even if you just had 2 chains, I give you the example of going up to 500 and something. You can set it for that, even though you don't have near enough links. You just set it to what the remainder would be, and so that's the way he would start it off.
Pretty cool.
Yeah. Thank you, Lafarr.